Thank you for having me. It's a pleasure to be here. So this is more of a reflection of when I was transitioning from the regular system design world to getting a lot deeper into the modern AI side of things. There's a bunch of mental model changes that I had to go through. I thought it would be useful to share a lot of it, assuming that most of you are builders here, and hopefully some of these things you are able to resonate with. I tend to think about systems design in this form. The science of characterizing fault models and the art of rendering those inert. That's where the engineering actually comes into picture. This is not a usual definition that we associate with when we think about systems design, but every single systems design principle can be mapped to a fault model. Let's take a few examples. Reasoning becoming too complex. Layered abstractions. Is this something that we don't see repeatedly? Be it the network protocols, be it the hardware, operating system, application, that kind of a hierarchy. So each layer doing its own thing. We tend to create these abstractions in place. This is one example of figuring out a system design principle to attack a particular kind of fault model. Another is isolating concerns. How do we make sure that when something breaks in a particular part, it doesn't propagate throughout the rest of the system? We tend to do that using modularity, right? Yet another example would be if we have, how do we prevent emergent failures from unpredictable interactions in a system? We tend to think about composability. We tend to develop an intuition about whether a particular component that I've created, is it composable or not? We tend to think about these terms repeatedly in systems design. And what I'm going to do in this talk today is that all of these principles have a basis in how we were building systems and what kind of systems we are building. And most of these principles do not carry over very well to the AI world. That is what I'm hoping to convince you about. The summary is fault models define the systems design. So if the fault models change, so should our system design principles. This is the struggle that I personally go through. How many of you have actually programmed in multiple languages? Most of you, right? So the first time that you moved from your original, the very first programming language to the next, didn't you go through a huge, like a mental block, right? You were trying to use exactly the same vocabulary, same practices, carrying it over to the next programming language, and you would feel that something is off. You're just not fitting in, right? And over time, it got resolved, unknotted, and you were able to make progress. Similar thing actually happens in systems design. So let's start with characterizing an AI system. I can rush through this thanks to all the talk that AJ did, Gura did, and Manish spoke about. Universal approximation theorem, it has been covered very well. I can save time here. The LLM, right? So we can frame a problem in a way. So notice the primitive. The primitive is just a function that predicts the next token based on a sequence of tokens before it. That's the primitive. Using that primitive, we are constructing a richer product. Okay. So this is like a happy prompting that I was doing with a particular LLM. I will not tell which one. So these are the predictions that it kept on making. This is not my doing, I can tell you. Okay, this is the LLM that actually threw up this kind of a prediction. Autoregressive LLMs is what we refer to these as. Manish spoke about why that is the case. This is the core primitive. I'm now talking from a systems lens. There's a core primitive, and we need to productize this into something useful. So instead of exposing this LLM directly to the user, we'll bring in some kind of an orchestrator in between. What it would do is it would keep feeding the generated output back into itself to keep generating a sequence of tokens which would eventually converge into a coherent sentence, right? So user's first input, is one of those things, but we usually prepend that input with a series of instructions which we refer to as the system prompt. This is something that most of you would be very familiar with. So what we do is we keep going through this loop almost. Notice what is happening here. There's two sources of knowledge that is coming into picture. One is what went into the training of the LLM. The second is the context window. And Manish spoke about a lot of it in terms of the kinds of context engineering that can go in, in order to almost coax out the knowledge that is hidden in the latent space of the LLM. We are like cajoling out that knowledge. All right. So there's a lot of really good work that can happen in the context engineering side of things. But the fact that there are only two sources of knowledge is something that we need to bear in mind. In terms of creating of all of this, there's a pre-trained LLM, which is like just dumping every single sequence of tokens that we can find on the internet, be it the words or the images. Often enough, we'll do some kind of a supervised fine-tuning on top of it in order to bring in additional domain-specific knowledge and things like that. And we'll do some kind of an alignment, some kind of an RL, preference optimization. So these are the ways that we try to tweak the knowledge and the behavior of LLMs. The fault models of AI are fundamentally different. Bear in mind, this very brief overview that I shared in the past few slides. Most of you are already aware about it. The three fault models I'm going to talk about are non-determinism, architecture, and those that stem from emergent behavior. Okay, but the principle is not limited to just these alone. The point that I'm trying to communicate is that the fault models of AI are different, and these are just some of those fault models that I'm referring to. Let's start with non-determinism. Okay? What do we mean when we talk about non-determinism? Probabilistic, right? This is one thing that we often tend to think about, but then we've dealt with probabilistic systems for a long while, haven't we? Right? We've had classifiers, we've had prediction models, all for a really long time. So what's different between that versus this? A major point of difference is that the output is open-ended. So fundamentally, modern AI, we are talking about what's possible, not just what's correct. Okay? And most of you would be aware about the fact that we do that by actually controlling temperature, which is essentially, instead of having a just very greedy sampling strategy, you end up sort of spreading it out and bring in a little bit of a serendipity to the picture, right? And that leads to a variety of different possible outputs, which is often what gets associated with this issue of hallucinations. Okay? But notice what is happening. Amongst the variety of outputs, some were correct, some were incorrect. These are not decoupled things. It's only when the output is not in line with what we expect. It could be a factual incorrectness, or it could be an alignment problem. We often refer to these as hallucinations. Okay? When the behavior is not in line with what we wanted. Until then, we were enjoying all the creativity. Okay? So it's almost like having a really, really good engineer in the team, except when they start speaking their mind, right? So it's kind of like that. The nature of this system is fundamentally different. Historically, every single system design principle we've had has been oriented to suppressing uncertainty, right? Every single moment in the laptops that we use, there are like hundreds of errors happening in the PCI interconnection that is on the motherboard. All of those is getting addressed via your standard checksumming methods. Same thing happens on the internet. Every single time we actually send a packet, there are many errors that are happening, and we deal with probability by suppressing it, by correcting for it. Okay. And what I realized was when I first moved into the AI native systems, as I like to describe it, my tendency for suppressing it, was really high. Okay? I wanted to control it, but I didn't want to suppress it. Okay? So what I realized was when I first moved into the AI native systems, as I like to describe it, my tendency for suppressing it was really high. Okay? I wanted to control it, but I didn't want to suppress it. Okay? So what I realized was when I first moved into the AI native systems, as I like to describe it, my tendency for suppressing it was really high. Okay? by the scruff of its neck until it becomes aligned. You better be aligned. Okay? I realized that it was the wrong approach to take. Okay? Fundamentally, instead of the strong control-oriented approach, embracing open-endedness in output, but having a mindset of alignment than control, that was a major mindset shift that I had to go through. Often enough, we will deal with some of this issue with, say, response verification. In fact, this is a very, very common practice where the output of the LLM goes through some kind of a verifier. There will be problems where we can create a verification method, and there would be problems where we don't yet have a good verification method. In case of code, the great thing is we already have a fantastic verifier, which is the compiler, right? If at least whether your code is structurally correct or not, we know, right? The compiler will tell you that. Even better, compiler usually points out where exactly is the issue. I can assure you, I can't assure you, but I have a very strong intuition that if the compilers were extremely poor at pointing out where the issue is, this feedback cycle would actually fall apart, and we would actually not be seeing extremely good output when it comes to code generation. Okay? So this is the kind of thing that we do. Ensuring correctness, response verification is one of those methods. We can do it in better training, we can do it in better prompts, and all of these are valid techniques. The main point here is that default model of AI, when we talk about hallucination, it's a feature, it's not a bug. That's personally what, how I, the statement can be debated. The takeaway that I want to emphasize on is embracing open-endedness in output is better than trying to control the behavior to a T. The next one, let's talk about architecture. Okay? There's a lot of alluding to this issue that I sensed in Manish's talk. What we have actually is a new computing substrate. Okay? We can think about an LLM as effectively CPU. Okay? Where the ISA, the instruction set architecture, the equivalent of x86 or ARM, that ISA has actually been created by the training process. Okay? And the context window, the content in the context window is your program. That is what is actually getting executed. Karpati, in one of his previous talks, I remember him mentioning this, and I feel this is a fantastic mental model to run with for anybody who's thinking about modern generative AI as a computing substrate. Okay? The only thing is this computing substrate is non-deterministic. Okay? It's very contextual. All the kind of system design things that we'd come up with before this are, we've always preferred context-free grammar. Most people in compiler design would actually have heard about this, right? Context-free grammar. Because if you bring in context, there's ambiguity, which goes against system design principles. So we tend to suppress, this kind of variability. But in the LLM world, or rather in modern generative AI world, it's all, we need to embrace all of these concepts, okay? But some interesting issues emerge, even if we were to assume this to be a viable computing substrate. For what it's worth, I'm a firm believer that this is a computing substrate, and we would see increasingly more methods of building systems on top of this computing substrate. That is the reason why I'm actually presenting this talk. Okay? So we have this LLM as the CPU. We've got the content in the context as the program. The inputs are the instructions. Prompt is the program. The issue is control plane is the data plane, right? Most of you would be familiar with how the separation between your operating system and your programs exists, right? That is supported, that is possible because the CPU actually guarantees a bunch of isolation boundaries, okay? some kind of, be it via page tables, protection mechanism, or, some of these things, it gives a privileged section and a non-privileged section. No such thing exists because we have not hand-tuned. We have not hand-written the circuit of the LLM. The circuit is emergent. Because the circuit is emergent, it's very, very tricky to actually bake in these kinds of boundaries. So effectively, the control plane and the data plane becomes exactly the same. Now, this is no different than how it used to be in the early days of compute. And I, for one, am super excited about what kind of architectural changes we can make towards bridging this kind of a gap, bringing in a lot of knowledge from the system side and trying to figure out how to apply those in the modern generative AI side of things and making it a genuine computing substrate. Okay? Because of this equality is precisely why we have prompt injection attacks. Okay? This is a paper, you guys can go through it, some simple strategies and stuff. But some other interesting things also come in, which you can see some kind of comparison with the normal systems that we build. So we have a fixed context window, we have a system prompt, user input comes in, things actually move out. Okay? A very naive way of implementing a context window. What does this remind you of? Buffer overflow. You guys remember from normal systems engineering, you have like a variable and you pump more data through some means you are able to inject more data than what that variable was supposed to hold, and you overflow the memory, right? So a very similar concept can happen here. Obviously, there are methods that we can use to sort of control this behavior by system prompt pinning or by summarization, a bunch of different techniques. But I found it very interesting how this analogy exists, which also means that the principle of trying to address these issues largely would come from the systems world. The third class of fault models stem from emergent behavior. So emergent behavior is anything which we didn't explicitly program. So consciousness, for example, we talk about it as being emergent. Life, we call about, depending upon whether you're a religious person or not, at least most rational people would agree that it is emergent. Okay? A bunch of atoms come together. The atoms were coming together not for the purpose of it, but things just happened in a certain way that a metastable state of sorts emerged. Okay? So what emergent behavior in AI does, remember that a trained LLM, a pre-trained model, is a CPU with its own ISA. Okay? What you can do is you can effectively program neural backdoors. Okay? So there are these papers where researchers went ahead and actually did that. Because the behavior of the LLM is emergent, you cannot deduce beforehand whether your model is backdoored. Okay, so you guys would remember this Marvel movie, where Winter Soldier or something, where a sequence of words you would say, and the mind of that agent became hijackable, right? A similar concept, researchers were able to execute in these papers. All right, the reason I'm talking about is, this is not something that we worry about today. Of course, we worry about, world over different governments breaking in supply chain and planting physical backdoors into the chips, etc. But at least there are techniques that we have developed over time through, X-ray scans and through, these kinds of things, which leaves some traces of, somebody interfering. This, because it's emergent, not possible. So we'll have to come up with new techniques to actually figure these things out. Okay? Another question is modularity. Okay? And I want to pose a question here. I'll give you a few options, and you tell me which one would be better, whether a modular pipeline or whether like a single model trying to answer that question. Okay? So I have this image, and I pose a question, like, what is jumping over what, if at all it is jumping? If I pose a question like that, do you think, so a modular pipeline might look like extract the image, segment out the object, remove the background, calculate distance, blah, blah, blah. How many of you believe that a modular pipeline would be better as against Like one model, just throw everything at it and let it infer. Okay, how many people for one model to rule them all? Okay, fantastic. Yeah, so great. So preaching to the choir. So yeah, I mean, that is the nature of the game. Modularity is an anti-pattern, a system design pattern that we've been so strongly trained on. I cannot tell you how much I suffer every single day. Okay, when much younger engineers sit with me, and I'm telling them, no, I'm like, break down this problem, and they're like, you're stupid. We can do this only in one model. Okay, so this mental shift that I actually had to go through is was significant. So our system design. The reason I'm sharing this is the system design principle that I carried over from my past is an anti-pattern. It's a baggage for me. I'm having to go through a significant mindset shift in order to build AI native systems. This one is actually trickier than the other two. How many of you would believe that a modular pipeline would be better here? How many of you would believe in the third image, the physics question one? How many of you would believe that it's better to take state-of-the-art text reading model and a state-of-the-art reasoning model and link the two? Okay. What if I had a really complicated pulley arrangement in the problem? Would your answer change? Likely, right? Suddenly, multimodality becomes super crucial. Okay? Again, modularity is an anti-pattern. It's much better to actually have those joint embeddings of sorts, that joint training of sorts, for the model to learn how to interpret things correctly. Okay? Composability, composability. So there's this very nice thing called MCP, which most of you would have heard about from Anthropic, referred to as the USB-C. I feel it's a pretty interesting branding. When I was thinking about are models composable, MCP was the first thing that came to my mind. Would you agree that AI world is composable? How many of you would agree that AI world is composable? How many of you feel that it's definitely not composable? Like composability is a challenge in the AI world. Okay, so most of you are actually somewhere in a superposition of states. The thing is, structural composability is an anti-pattern. Structural composability without reasoning composability. The thing is, you can provide different channels for the single brain to reach out and use a tool or get data or read from your database or send an email. That is structural composition. But so long as the reasoning is happening in a non-decomposable way, you cannot call it composability. Okay, that's my proposition. Obviously, you guys would have different opinions. I remember the specific the slide in Manish's talk about composability, about where a cross attention as a way for achieving that. I am a lot more bullish about those kinds of techniques. But the point is, we have to come up with different techniques about composition than the API-centric composition that we normally do. Okay, again, system design principle not carrying over very nicely to the AI native world. We have to make that transition in a very different way. Okay. So to summarize, AI native systems are in a new class of their own. Hota kya hai, every single time a very new foundational thing comes into picture, we tend to just force fit into our old way of doing things. Okay, I have done the same enough number of times. I continue to do the same enough number of times, but I recognize that it's a barrier. So every one of you who's actually a very good systems engineer, I'll encourage you to acknowledge this unlearning process that we actually have to go through. Second thing is, fault models of AI are very different, and that's why we need to come up with fantastic new systems engineering principles, and that's the opportunity. I feel a lot of engineers with a systems background, like people like me, you would actually be interested in. There's a lot of new computing paradigm that is available. Like a lot of new stuff is going to get created. And that's something that I'm super excited about. So yeah, that's a summary of my talk. Thank you so much.